In section 1-2 on composition of functions, the important material to come out of here knowing is how to combine functions by adding, subtracting, multiplying, dividing, and understanding their domains, but also doing a composition of functions. Now, we're going to do a composition of functions that's a real-world application, but the reality is we want to learn the basic mathematics so we can understand how to apply it to the application. So let's start off with the adding, subtracting, multiplying, and dividing of functions. So the definitions we learn for combining functions: the sum of two functions, this is pronounced f plus g of x, is just adding two polynomials together. When you add two polynomials, you just add the like terms. The difference of two functions is really just the same as the difference of two polynomials. The product of two functions is the same as the product of two polynomials, which requires your FOIL if they're binomials or any other polynomial distribution. The quotient of two functions, the only thing you need to be careful about is when you have a fraction, the denominator cannot be 0. So let's add two polynomials in this first example. If f of x is 2x plus 1 and g of x is x squared plus 2x minus 1, all you're doing when you add them is this. Notice the parentheses. Adding two polynomials was just adding like terms. So 2x from the first polynomial is a like term of 2x from the second polynomial. When you add them, you get to 4x. And 1 and negative 1 are both like terms because they're constants. 1 plus negative 1 is 0. The only thing I didn't have something to combine with was the x squared. And because I like to write things in descending order of powers, I'm going to write the x squared first. So when you add the two functions, you get x squared plus 4x. However, when you're subtracting two polynomials, we're going to use the same two polynomials, you have to be kind of careful. Let's go back to the fact that I put them in parentheses a few moments ago. You might recall from Algebra 1, your Algebra 1 teacher might have told you to do one of two things. Either they told you to make this a plus sign and to change all the signs here, or they might have told you to find your like terms, and the only thing was you were going to subtract them. I'm not sure how your Algebra 1 and Algebra 2 teacher did the problem. This is not my preferred way of doing it, but I do it both ways. So hopefully I've hit all my bases. I'm going to go back to the way that I was doing it because I'm particularly fond of distributing the negative to everything inside the second parentheses and then adding the polynomials together. So you'll notice this time when I combine my like terms, the terms with the x's are opposite, so they cancel when you add them. 1 and 1 is 2. And there was nothing I could do with the negative x squared, so the answer is negative x squared plus 2. What if I want to multiply them together? Again, look, I put them in parentheses. You have to use distribution. The way that I like to do it is I like to use little arrows, and I start with the 2x, and I multiply it by everything in the second parentheses. So I get 2x to the third, that's what 2x times x squared is, plus 4x squared minus 2x. And then after I'm done distributing the 2x, then I'm going to go and I'm going to distribute the 1. I get plus x squared plus 2x minus 1. One of the things I want you to notice is how many terms I got when I was done multiplying. I got 6. Well, if you add the terms, if you multiply the number of terms from the first parentheses with the number of terms from the second parentheses, doesn't 2 times 3 equal 6? It's a nice check to make sure that you multiplied correctly. Now I'm going to go back and I'm going to look for any like terms. Let's see. These are like terms, and these are like terms, and those are the only like terms I have. So I get 2x cubed plus 5x squared. Negative 2x and positive 2x cancel, minus 1. Now we're going to find the quotient. And what we get depends on which function is in the numerator, which is in the denominator, because we have to determine what the domain is going to be. I'm writing this in two different ways, just so you know. Both of these notations really say the same thing. The first one, f of x over g of x, and g over f, so that should be an f. There we go. G over f of x. It just depends on which function goes in the numerator. Now, I've used some radicals here because that gives me a chance to go back and talk about domain for a moment. Again, something we did in Algebra 2. So let's start with f over g of x. I'm just going to put this in the numerator, and I'm going to put this in the denominator, and that's the answer. Wow, that was easy. There's no simplifying. Yeah, technically there is, but it's for something we might do in an honors class or in calculus. We normally don't like radicals in the denominator, but yeah, we're not worried about it here in the regular pre-calc class. What I am worried about is the domain. All right, so here's the deal. Let's look at the graph of the square root of x. Here's the graph of the square root of x, which I did on Desmos because I think it looks really nice. So I want you to notice that the function starts here at the origin 0, 0, and then it goes off to the right. Now, even though you don't see an arrow, there really is an arrow there. Domain only refers to the x values. When I'm looking at a graph and I'm trying to determine the domain, we say that x is greater than or equal to 0. We have another method of writing these types of inequalities. It's called interval notation. We might also see it like this. I'm not sure if any of you saw this in Algebra 2. This basically says that it starts at 0, and it would be a closed dot at 0 on a number line, and then off to the right it goes to infinity because it goes to the right forever. That's what the graph says. Either one of these is okay notation. So let's go back here for a second. The domain, oops, I'm getting rid of stuff that I don't want to get rid of. Okay. The domain of f of x is greater than or equal to 0. Now we have to go look at the domain of 4 minus x squared. Here's the graph of the square root of 4 minus x squared. I want you to notice that the x values, I don't care about the y values, the x values go only from negative 2 to positive 2. In inequality formation, notation I should say, it would look like this. It's called a compound function. We say that it goes from negative 2 to 2x's between them. In interval notation, if you learned that, it looks like this. All right, so now let's go back here. And here's the domain. So, two things are going on here. There's the fact that all the x values have to be greater than or equal to 0 because you can't take the square root of a negative. And in the denominator, the domain has to be everything between negative 2 and 2. If both of those things are going on, what we want to find for the domain of the new function is the intersection of those two functions. How did we find the intersection? Well, the way you probably learned it was to do it on a number line. So one of your inequalities was x is greater than or equal to 0. It was a closed dot on 0 going off to the right. I'll do the other one in red. The other one was from negative 2 to positive 2. The way I used to teach this to Algebra 1 students is I would say, well, where's the intersection? Where do the two graphs overlap each other? Well, they overlap each other from here to here. That means that the domain of the new function must be between 0 and 2. So first I had to find the domain of f of x. Then I had to find the domain of g of x. And I'm particularly fond of using the graphs to help me find domain. And then, in order to find the domain of the new function, I found the intersection of those two domains. I'm going to do this again for g over f of x. All right, let's find a different color. All right, so if instead I put this on the top and I put this on the bottom, wait a second, the domains of each individual function is the same. That means that the domain is going to be about the same. However, there's one little minor difference. And the one little minor difference is, in the first function, f of x over g of x, what happens if you plug in 0 for x? Well, the answer is you get 2. All right. Now let's go back to the new function. What happens when you plug in 0 here? You can't do that. Well, remember on the number line the difference between open circle and closed circle? We would have an open circle at 0. That would use this symbol instead. But you can plug in 2 for x because 2 actually works. So you'd have a closed circle at 2, which is why we use the inequality symbol with the line underneath. I should go back for a moment to this first one because this is incorrect. Not that one, sorry. This one is, man, I'm having a problem here. All right, this one is incorrect because you can't plug in 2 for x. What happens when you plug in 2 for x into the new function I wrote in blue? You get the square root of 4 minus 2 squared. Well, 4 minus 2 squared is 4 minus 4, which is 0, and you can't have 0 in the denominator. So what's going to end up happening is that I need to use the symbol for open circle instead of closed circle. I apologize for that. Sometimes I mess up, just like you guys do. The point is that I went back and fixed it. So the domains were close to the same. The only thing different was where you had open circles and closed circles. Remember when we learned how to do this, it was the difference between the inequality symbols with the lines underneath and the ones that didn't have the line underneath. The thing I want you to notice about the compound inequalities, notice that the compound inequalities are always pointing to the left. All right, we're going to call that part 1. I'm going to go back and change this because I want to end this video and I want to do the other part, which was the composition of functions, in a different video.